we'll post our first homework after today's lecture. So after we learn something rigorous. Okay. So let's continue our geometric interpretation of the gradient of a function. So last time we learned like the gradient is where this function in the direction that a function increases fastest. And so today we'll first learn more geometric interpretation of it. So we'll introduce a concept called a level set. All right. So again, so our function of interest, okay, is a function from Rn to R. So it means f, so this x right here, okay. So this x here is an element of Rn, and the output is a constant. So let's say this constant is A, and this A is a scalar, okay? And then we can define the following set. All right? So how to define the following set is the following. That is, we define the collection of points in Rn such that so we define such a set, and this is called the level set of F. So it's called all right. So using this 2D, the simplest example. Okay, so think about. So by the way, here x, y are respectively like what? Yes.
What is the constant?
Yes, c is a constant. Thank you. So so where? So and c is used as the subscript of this set because for different c's we have different x's, so we have different sets. So for example, so let's use our favorite quadratic function in 2D. Okay. Let's still make this d. So we have parabolic surface. Okay, so if we look at the graph of this function, it's a surface in 3D. Okay, because think about x and y are the location of the spatial location. Okay, and the function value is our altitude. Okay, so we're climbing a hill, and we're going down a hill, and so spatial location and altitude. And now what happens is we set, okay, think about it. Think about this level set. All right. Have several cases. Okay? So when c is less than 0, set is an empty set. Because a quadratic function with only quadratic term, like this is quadratic, can never be less than 0. And when c is 0, so apparently that the only numbers will make this 0 is 1, 1, and we have a single point. And when c is, the most interesting case is when c is greater than 0. When c is greater than 0, so if we, I'm going to copy this again. So when c is greater than 0, if we look at this equation, so when c is greater than 0, the square root of c is the radius of the circle represented by this equation. Okay? So then what happens is this level set is the circle with radius square root of c centered at 1, 1. Okay? But I mean, it's a circle, but the message here is this level set. Okay, so this level set, the set that describes the axis in this set, is a smooth curve. Okay. So in 2D. Think about it in 2D case. In 2D, so SC is a smooth curve for smooth F. Okay. So what do we wanna like leverage from this is we want to get another like physical interpretation of the gradient. That is, now what we can do is we can parameterize this curve. Okay. So it's a curve. Think about it. The curve is a 1D object. Okay. So we need to adopt this thinking that it's intrinsic dimension. For example, in machine learning, we always talk about intrinsic dimension, So one neural network can capture, for example, can generalize so well is it captures like the intrinsic low dimension that's living in a high dimensional world. For example, well, in 2D world, what this curve is actually a 1D object. What does it mean is we can parameterize this curve by a function. So by what? By the graph of a function t. So by this g of t, okay, with parameter t that is r. So at least locally. What it means is if we draw, for example, the level set of this smooth function, so we examine this part, okay? So we examine this part. So this curve right here, which is a part of this level set, so this part is the graph of a single variable function. Okay. All right. And this g of t, okay, and this g of t not two.
are you saying that we should always parameterize along the curve, not like you can parameterize with respect to the angle that it makes too, but you're saying here that we prefer to parameterize it along the curve.
You can parameterize using angle.
Okay.
So this parameter can be angle, it can be any other number.
Because yeah, if it's angle, then we can have it continuous, but if it's along the curve, then yeah, we can.
Yeah,
do it
but
locally.
that's
Okay.
why I put locally,
Okay.
because
Yeah.
we cannot parameterize
Yeah, we
the
can't
whole
parameterize the
curve
plane.
using a single
Not along,
parameterization. But, yeah.
not along the curve.
Yeah,
Okay.
but I try to avoid the technicality, that's why I put it locally here. So, for example, this is a vector function.
Mhm.
Okay. Now, if we look back at the level set's definition, so the level set definition is f of x. Oops. Is 0. Okay. Sorry. Is c. And for x in this level set, okay. So that's kind of, because we define this using this, but then this equation holds for all the points in this set, okay. Now what we can do is we can rewrite, because we can parameterize this set by this vectorial function. Okay. All right. So because SC is parameterized by G of T. Okay. Wow. So it's a constant, right? So this is a constant. It means this function. So when we view this as a compositional function of t, so we view this f composition with g of t is a constant. What does it mean? Is the derivative with respect to t is 0, right? It doesn't change with t. So when we move along this curve, our altitude doesn't change. So it's like going on a trail, or going along on the same altitude, it doesn't change. So let's take derivative here. Okay. So when we take the derivative with respect to t, okay? Now we'll use chain rule. So if we use chain rule first, we take derivative of f, okay? So this is chain rule. Let me write out the chain rule. We take derivative of f, but f takes input of vectors, so we have to take the gradient of f, but evaluate it at, this g of t. And then the chain rule dot product. So g is a single variable function, but the output is a vector. So this is like g prime of t. Okay. So this gradient is a vector in Rn, and this prime, okay, so even though it looks like a scalar, but because g is a so in this case it's R2, but in general it's Rn. So this is an Rn. Okay, so this is a dot product, or inner product. Okay, so this is 0. Okay. Now we have another interpretation of the gradient. So we can write something like this. So the gradient, okay, of x inner product or dot product with G prime is 0. So this is our gradient. What is G prime? G prime, when we talk about this, so this part. So for example, the vector, the position of the points along this curve can be written as G of t equals x of t, y of t. So when we take derivative of G, it's x prime of t, y prime of t, and this actually represents. So without all loss of generality, let's assume we move from this point to this point, which means this point, maybe say t equals 0. Okay, so at this point, t equals 0. At this point, maybe t equals, I don't know, like, let's say this angle. Let's say at this point it's pi over 6. Okay? So this direction is the direction of t increasing, then at this point, G prime actually represents. So this is G prime of t. So G prime represents what? G prime represents the tangential direction of the level set curve. I mean, it's a curve in it's a curve in 2D, but in general, in ND, we call it a hypersurface. But we can always, take a step back and use this example in 2D. And using this climbing hill example, using the climbing hill example. So when we when we walk on a trail that, our altitude remains a constant when we climb a hill. So, for example, so we walk, along the trail. We walk essentially in the tangential direction. Okay, our altitude doesn't change. But when we make a turn 90 degrees, that is perpendicular or orthogonal to the tangential direction, we either look at the steepest descent direction, which is rolling down the hill, or the steepest ascent direction that's climbing up the hill. So think about a real life example. Okay. So this is another geometric interpretation of the gradient. That is, the gradient is orthogonal. So the gradient is orthogonal. So this is another geometric interpretation, the second geometric interpretation. Is the gradient is orthogonal to the tangential direction of the level set. So in calculus we actually derived in vector calculus. So we actually derived using we derived an equation of a tangent plane using this, but I guess in calculus without this explicitly spelled out. So the main topic today is we'll learn so today we'll make things rigorous. So I'll restart this numbering of panels. Okay. So we'll make things rigorous. So last time we'll like the introduction. So today we'll learn local minimizer and their conditions. So again, let's review. Let's review a problem we're interested in. So this is a problem we're interested in. We want to minimize the function such that, or subject to, x in the domain. Okay, and but think about this. So this is our goal, but we have to know whether we can achieve our goal, and for specific f's. So for example, so let's draw using a 1D example. Okay. So today we'll formally define local minimizer. All right. So for example, this point is a local minimizer. Okay. This point is a local minimizer as well. And all these points may be served as a local minimizer as well. So for example, x1, so this point is x2, and this interval may be I, and for all x in I, so all these points are local minimizer. Okay, so x1, x2, and x in I are local minimizer. And we want to rigorously define this local minimizer. So first let's look at global minimizer. So we say x star is a global minimizer. Is equivalent to say what? Is equivalent to say for any x in omega. Okay. So this sign here means for any or for all. Okay. So for any x in our domain that we want to minimize our function, f of x is greater than or equal to f of x star. So the English translation of this is, okay, star, x star, f achieves, the lowest value at this point. Okay. So if we want to add a strict...
So we're allowed to have multiple then, because that wouldn't exclude multiple value with x star, as long as they evaluate the same lowest level.
This doesn't exclude multiple value of x star. Okay. So if we can add a perfect strictly global minimizer, then we change this condition to f of x that is greater than this. So by the way, this condition doesn't guarantee there exists such a thing. Okay. So this says, okay, so if this condition is satisfied, then we call this point x star a global minimizer. Now we look at local minimizer. Okay. So if we look at this graph, okay, so let's first, so over there, we give this like mathematical definition first, and then we try to translate it into English. But here, local minimizer, let's give the English translation first. So local minimizer means this point is only the lowest point locally, like around the neighborhood, okay? So for example, this point is the lowest around its neighborhood. So local minimizer, so x star, so f of x achieves the min value at x star among its neighbors that are near. So this is the keywords, that is near x star. Okay, so this is the English translation, but how near? How do we use a mathematical formula? You know, how do we use a mathematical strict statement to make this rigorous? Okay, so we say now we define this local minimum. So we say x star in omega is a local minimizer if the following things is true. That is, there exists an epsilon that is greater than 0. Okay, so this notation, like the mirror image of E, means the following thing. So there exists an epsilon that is greater than 0 such that, okay, for any x in the following set. Okay. In what set? In the set that's near x star. And how near? The distance is less than epsilon. And in this neighborhood, the function value is greater than or equal to x star. So this is a mathematical strict definition of local minimizer. That is, so this translates to, for any x in the neighborhood, so this inequality means it's near, where is that? X star, okay? And in this neighborhood, the function value is the smallest at x star, and we only need the existence of such neighborhood.
So in your graph over there, and you've got your level line, and then it goes down level back up. If instead of going down level back up, it's down level and then down, anything within that level line, we could, by this definition, we can call a local minimizer, because we can find a neighborhood about that point, but except for the point itself where it starts to turn down, because there would be no neighborhood about that actual point where it starts to turn down.
So in this diagram, there are no other local minimizer other than here, here, and here.
Right, that's what I'm saying. So if you take the edge of your curve where it goes back up, so that entire flat area is level. Because at any point along that flat area, but if instead of that flat area, instead of going back up at the end, it went down, we would have an open point there.
Yes,
that would not be a local minimum. I mean, that would be a point we'd have to take out because we can't get a neighborhood about that.
Okay, yeah, that's a good point. Yeah,
Okay.
yeah. We actually will learn these conditions in a moment. So yeah,
Okay.
so
anything other than that, we'd be okay with.
yes,
Because we can shift over to any small amount and find a ball. Okay.
That's true. Okay, so this is a mathematical reverse definition. Okay. So, but inspired by this gentleman's comment, let me make additional restriction here. So an x is not x star. For any x that's in this set, but that's not x star, this value should be greater than this f of x star. So now let's learn. So the main topic of today's class is we try to.
If x is not equal to x star, and then why we write equal here? I mean, where is equal? Where we find the f of x is equal, f of x is equal?
Okay. So this lady's question is, if x is not x star, okay, how this equal sign is achieved? The answer is this equal sign doesn't have to be achieved. Okay. So strict inequality is still like a subset of this greater than or equal. So yeah, it doesn't have to be achieved, the equality sign. So this condition is satisfied doesn't mean the equality has to be satisfied.
So why we are giving that symbol? We don't need to give it, right? So if this we specifically don't need the equality.
We don't need the equality. That's
So-
true. So for example, so let's use.
So that's the question again. That's the same. Over there you have written equality, but again not equality.
What I mean here is
Strict.
there is a definition when we talk about strictly global minimizer. This
Oh,
is greater than or equal.
Okay.
So for example, this. So which we'll add here. So if we have a strictly local minimizer, then everything changes. This changes. This condition changes too. So everything is the same. Everything is the same, and this condition changes to f of x that is greater than x star. So for example, so these 2 points, are strictly local minimizers. And this is just a local minimizer, it's not a strict local minimizer. Okay. So now today, we'll learn several things.
So these are local because there are multiple values. That's why.
You mean here?
Yeah.
Yeah, here it's because in the neighborhood. So here, why it's not strict is because in the neighborhood. So there exists such a neighborhood that equality sign is achieved.
Achieved. Okay.
For it to be a strictly local minimizer, we can only have strict inequality. Okay?
1 point.
Yeah, we only have, like you said, 1 point. Yes. Okay.
Yeah, it's a complex function, then we're done. Because
And,
complex function is constant in any interval, is constant globally.
So now let's continue. So today we'll learn basically we'll formalize what we learned the last time. We'll formalize first derivative test, second derivative test, and we'll learn what are the necessary conditions and sufficient conditions. Okay, so now let's first recall some logic. So if statement of A implies B, okay. So A is a sufficient condition for B. All right. So B is a necessary condition. Okay. So we can have many, for example, when we learn philosophy, we learn lots of these weird things, but let's use some specific example. So the statement that A is, is what? Is X is an even number. Okay. So B is, so X is an integer. So this says X is an integer. All right. So X is an even number means X equals to N for N is an integer. So apparently, if A is an even number, A must be an integer. So A being even is a sufficient condition for X being an integer. So it means if X is even, then X must be an integer. So then the B here, X being an integer, is a necessary condition for X to be even, because if X is not an integer, we cannot even talk about it's even or odd. Okay. So today we'll learn two types of condition, that is necessary and sufficient condition for X star to be a local minimizer. So the first condition we learned is called first order sufficient condition. Think about this as our first derivative test, but in a much more general fashion than the first derivative test we learned in calculus. So let's say Funko something. First order. Wait, I want to do necessary condition first. Sorry. So first order necessary condition. So Bjorn. So if X star is a local minimizer of F, okay. So again, we are interested in this problem. Okay, so always think about that problem in mind. Then, for any feasible direction, or admissible in some textbook, it's using admissible. So for any feasible direction, D, so D is an Rn vector. So for any, so I'll explain the feasible means. Okay. So for any feasible direction, the gradient of F evaluated at this local minimizer, dot product or inner product with D is greater than or equal to 0. So, and other, in other textbook, we may also see, using this gradient transpose of D, or even D transpose gradient of F, which I'm not a fan of this notation. And sometimes you even see something like this. Okay. So in any optimization lecture notes, maybe other people use, but I mean notation-wise, all of these are the same. But the point is, for any feasible direction, this is greater than or equal to 0. The interpretation of this is, think about this. This is the rate of change of f at this point in this direction. Okay, so this is a directional derivative. D is a direction. Okay, so this is a directional derivative of f at this point. If in every possible direction, the directional derivative is positive, it means we move from this point, our function value increases. Okay, so then intuitively this, so the directional derivative is greater than or equal to 0 in every direction. So now let's explain this, what feasible means. So feasible just means there exists an epsilon that is greater than 0, and for any alpha that is greater than 0 and less than epsilon, okay? So x star plus alpha b is still in this omega. So so for example, some non-feasible direction, so think about, so if we are in omega, all right? So if our x star is here, which is perfectly possible, because last time we verified, when we have a bounded domain, the minimizer is either achieved at the local critical point or on the boundary. So if we're at the boundary, okay, if this is D1, then D1 is a feasible direction, because when we move a tiny step along this direction, we're still within this domain. Okay? So this direction is feasible, but this is not D2. So this is not a feasible direction. Because no matter how small our step is along this direction, we'll step out from this domain. Okay? So the feasible just means.
So we need to be in domain to calculate that.
Say it again?
So we need to be in domain to find the direction.
Yes, yes. So what this gentleman suggests is we need to be in the domain. So another typical example is here. Okay, maybe this is D3. Okay, so if we move along D3, we move far enough, we get out from the domain. Okay, but if our step is small enough, it means it exists. So if we move long enough, we still get out of the domain, but there exists an epsilon such that if we make a small enough step, we're still within the domain. Okay. So the not feasible is basically negation of this statement. So not feasible just means the direction not feasible means for any epsilon that's greater than 0, okay, and there exists an alpha that's between 0 and epsilon such that This is not in omega anymore, okay? So no matter, this just translates to, no matter how small a step we make, we step out from the omega. And this alpha has to be greater than 0 for a reason, but I don't want to go into the detail of that because that involves open and closed sets. So it's beyond the scope of this class. Anyway.
So can I ask? So the alpha, so omega needs to be in a small step.
What do you mean by omega?
So, sorry, the
Alpha.
Alpha.
Yes. So alpha has to be a small enough step.
Small step.
Yes. So it's like if we take a small step, because later when we do the analysis, we'll find eventually we will restrict our alpha to be very small.
Okay.
Which is like alpha is like our, for example, the step size or learning rate in gradient descent algorithm. You know, must be small.
Okay.
So now let's prove the theorem. Okay. So we'll use our Taylor expansion again. Let's recall. Yeah, let me write down the formula right here. Okay. So let me write down the formula right here. Taylor expansion. So f of x plus ab, so plus alpha d. Okay. So d is in Rn. So x is in Rn, and alpha is a step in R. This is f of x plus alpha gradient of f of x transpose d, okay, plus big O of alpha square, so Taylor expansion of the first order, and Taylor expansion of the second order is this equals f of x plus alpha gradient of f x transpose d plus 1/2 alpha square d transpose Hessian of f at this point d plus big O of alpha cubed. So today we'll mainly use those two tools. So now let's look at the proof. So for D, so let's consider D be a feasible direction at x star. Question about the formula?
The second one is how it's just f of x plus ad. That isn't like f prime or anything for like the second.
Sorry, this is alpha. What's your question again?
That like isn't the second derivative or something like f prime.
Here is the second derivative. The Hessian.
Oh, that's all one line.
Yeah, sorry.
Okay.
It's
Okay.
all one line. Sorry. Right. So why we have to the technicality reason that we have to restrict ourselves to consider a feasible direction is we want this guy to be still in omega to talk about this f of this thing. Okay. So now if we look at this, so this equals, so by first order Taylor expansion, so what we have here is plus this is alpha gradient of f star dot product with d plus big O of alpha squared. So now if x star is a local minimizer, then that means for any feasible direction d, so for any feasible d, this guy is greater than this guy. Okay? If we move this f of f star here, it means so we subtract x star to the left, it means this is greater than 0. Go
Is
ahead.
that AD or alpha?
Alpha, alpha. Thank you. Yeah, it's alpha, alpha. Yeah. Okay. So this thing is also alpha. Okay. So it means for any feasible direction d, this is true, but there is a restriction. That is, we only want to consider for sufficiently small alpha, because the local minimizer says we only have to find such a neighborhood. Okay. So our goal is we restrict ourselves. Okay. The reason to do this is we want to restrict ourselves in the small neighborhood. Here in the definition of local minimizer.
Why we can't ever alpha order of alpha square? Because we say alpha is sufficiently small.
Yes.
So why consider alpha square?
Yeah, we want to make it strict. Yeah, we'll talk it in a moment. So for example, what we want to do is, for example, we can let, okay. So for example, what we can do is we can let alpha to be a number such that alpha times this direction is less than this epsilon. So now what happens is we can conclude that, so because this guy, okay, so this guy, so first of all, alpha is greater than, so alpha is always greater than, so when we do something like this, so for any alpha, okay, so for any alpha, this whole thing has to be greater than or equal to 0, and we want to show that this thing is greater than or equal to 0. Okay, even plus this guy. Okay, this thing cannot be negative. So if we assume, I mean, this is a simple proof by contradiction, even though from here it's already obvious, but we still want to write this down. So it's, if we assume this is negative beta such that this is less than 0, okay? Then what happens is we can always find an alpha, so then we choose alpha such that this big O alpha, okay, is what? So we can always choose alpha small enough such that this big O of alpha is beta divided by 2, and then is strictly less than 0. Okay, so this is a contradiction. So this is what it means. So this actually implies has to be greater than or equal to 0. Okay.
First question, does it matter if it's the order of alpha or alpha squared? Because you kind of, I don't know if you meant to leave the square off or not.
No, I pull out an alpha in front of it.
Oh, okay.
So we can pull out alpha. So alpha.
Okay. And then can you explain why it's a contradiction one more time? I just don't see it.
We have this guy has to be greater than or equal to 0.
Mm.
Yeah.
But now, if we assume it's negative, this we can choose an alpha such that this is negative. So it's a contradiction. This thing has to be always greater than or equal to 0. Alpha is positive. So this difference has always to be greater than or equal to 0 in order that x star is a local minimum. Okay. So this thing by Taylor expansion is this. So now we want to show this has to be greater than or equal to 0. So now let's assume it's less than or equal to 0. So it's a negative number. But if it's a negative number, we can choose a small enough alpha such that the sum becomes negative. But once this is negative, it contradicts with this thing has to be positive. Okay. So it's a contradiction. Okay. So this is the first order necessary condition.
So I have a question.
Go
If
ahead.
it's contradict that, what does this define? This line, the last line you've written.
Yeah, because it contradicts, right?
Yes.
So if our assumption of this leads to a contradiction,
Yeah.
then our assumption must be wrong.
Okay.
So our assumption,
Assumption.
so the negation of our assumption must be right.
You're wrong.
So our assumption is this guy is less than 0 is wrong, then this must be right.
This means right.
So
Okay.
now
Okay.
we've finished our proof of this here. So this is go ahead.
Why is alpha is small, okay, but why is alpha order of alpha is equal to beta? How we use beta? That's beta. And, I mean, why is it beta like this?
Okay. So we can assume this big O alpha is like a function of alpha. We can simply do that. You know? And this G of alpha is a function that is linear in alpha. Okay. So this is like a G alpha equals a constant times alpha. Okay. So G of alpha equals a constant times alpha. Right. So we can always choose alpha to be small enough so that.
What about C? We can choose anything.
Say it again.
We can choose what about C?
Yeah, we chose beta divided by 2 so that their sum is negative. Yeah, it's a convenient choice. You can choose others. So here is, we assume actually this guy is positive. Because if this guy is negative, this is automatically correct. Okay. So if this is negative, we can plus this here, and this is already automatically greater than or equal to 0. So what we want to do is we want to show the case that when this is non-negative, this is still true. Okay. So, okay, now let me make it even more obvious. So let's start from here. Okay. Let's start from this proof right here. So we know that so this is big O alpha. So big O alpha is big O alpha is basically a linear function of alpha. Okay, so let's say this is capital C of alpha. All right, so let's start from here. So if, okay, so if C alpha is less than or equal to 0, then we can subtract this 2 here, and it's greater than or equal to 0. So then alpha of this, we subtract this to the left. Okay? See, alpha is less than 0, alpha is positive, so this is, that means this is already correct. Okay, so the key part is if C alpha is greater than 0, we want to show this guy is still non-negative. Okay, so, but it's difficult to argue directly, so that's why we use contradiction. So now, if now we assume, so now we use proof by contradiction. So now we assume that this is a negative number. Okay. So it's a negative number. All right. So now what we want to do is, because this is a fixed negative number, but alpha is like arbitrary. So now alpha is at our disposal. We can choose an alpha that leads the contradiction. So this is just, so then we can choose, because alpha is arbitrary, we can choose an arbitrary small alpha such that C alpha is beta divided by 2. No matter how, whatever this beta is, you know. So as long as it's a positive number, we can always choose a sufficiently small alpha such that this is true. Okay? And then it's this line. Okay? So we choose this is beta divided by 2. This is negative beta. This is beta divided by 2. I mean, we don't have to choose beta divided by 2. We only have to choose this is a number that has a smaller magnitude than this guy. Then, you know, it cannot. So because this is only like beta divided by 2, if we choose a small enough step size alpha, this cannot negate the impact of this being negative. So this overall is negative, which contradicts with our local minimum condition. Okay? So that's why it contradicts, and this guy has to be positive, and this is a necessary condition in order that the local minimizer is achieved at x star. So it's a necessary condition because we start from x being a local minimizer. Okay. So this is like so A implies B. B is a necessary condition for A. So A is x star is a local minimizer, and B is this state, right? So now let's look at second. I mean, we don't have time to prove it, but let's motivate the second order necessary condition. Because so we have to be be crystal clear about one thing. That is, necessary condition doesn't mean sufficient condition. Okay. So okay. So when this is true, we have two scenarios that this is true, right? Because here, we only can prove, I mean, this is the strongest possible thing we can prove based on, you know, based on the local minimizer definition. So it is possible that we have two scenarios that one of this is a strictly greater than 0. It means when we move along every direction, when our step is sufficiently small, our function value will increase. So this is indeed a local minimizer like for sure. So this can be a sufficient condition. So we will prove it next time. So, okay. But there's another scenario that is, what if? It's a critical point. So this can actually, you know, be other things. For example, we can have a saddle point at x star. Okay, not necessarily local minimizer. So we can have a saddle point. So this is not a necessary condition. It's only this is not a sufficient condition. It's only necessary. So for example, when this is true,
can we say it's like a special condition if equal to 0?
so this condition is necessary. It means in order that x to be a local minimizer, this must be true. Okay? But it's not sufficient. It's because when this is true, x star is not necessarily, so this condition, so what we just learned, is not sufficient. The reason is because when this is true, one possible scenario is this, okay? Then another, so within this condition, a possible scenario is x star, the saddle point, and saddle point is not a local minimizer. So saddle point is when we view from one direction the function increases, but when we view in another direction the function value decreases.